So I do computer vision and machine learning, and computer vision is basically a subset of artificial intelligence where you're dealing with images or video and you're trying to understand what's going on, what's in the image, what's in the video, what's happening, what's the intent of the actors, what can you see and what can you infer from this. And from in the old days, people thought like, well, if you want to learn to recognize an apple, then you should try to define its geometric and visual properties. Like an apple is approximately a sphere and it's approximately red and so forth. And for 20 years in computer vision, people did things that way. And the short version of the story is it doesn't work at all because apples are not really round and they're not really red. And it's actually quite complicated to describe what's an apple or what's not an apple. So that necessitated the bringing of learning systems into computer vision, where you're training systems by example. So like, here's 1,000 apples, here's 1,000 oranges, here's 1,000 lemons. Now let's see if we can learn the differences between these things. So that really ramped up in like the 90s, 80s and the 90s. And I started my PhD program in 1995 at MIT, and there were a small number of people who were trying to get computers to learn at the time, to learn in order to be better at computer vision. But one of the interesting things about the early work in computer vision is people were trying to get as much data as they could to teach a system how to recognize something. So if you wanted to recognize the difference between dogs and cats, you try to get 5,000 pictures of a dog and 5,000 pictures of a cat, and then build a program that searched for the things that were true of dogs and not true of cats, and vice versa. So supervised learning is this basic process where you provide examples of different classes and you try to get the computer to differentiate amongst them, okay? Now, when I was in grad school, a lot of people were focused on this problem of recognizing handwritten digits, right? Like, can you tell the difference between a handwritten 0, 1, 2, 3, 4, and so forth? So that's one of the classic supervised learning problems that machine learning and computer vision people have focused on. And when I was in grad school, people were using 6,000 examples of each digit class to train their classifiers. So, 6,000 zeros, 6,000 ones, 6,000 twos, and so forth. That's an awful lot of examples. And these systems, after they were trained on these examples, could do really well on new examples. They might get 99% accuracy or even higher. And a lot of the research was focused on going from like 99.3% to 99.4% to 99.42%, and it was getting kind of ridiculous. They were just making these tiny advances. And at that point, the new euro symbol came out while I was in grad school. And when I saw that new symbol, it just struck me like, I don't need to see any more of these. One is enough for me to have a good idea what this thing looks like. And I'm going to recognize it in different fonts, different colors. If it's tilted to the side, none of that matters, right? I only needed one example and I'm all set. I could get near 100% accuracy now. So it just sort of struck me, we're focused on the wrong thing. We should be focused on the fact that humans can learn really effectively from one example, where if I gave something like a neural network one example, it would fall flat on its face and just do terribly. One-shot learning or low-shot learning. It's a machine learning paradigm where we focus on learning problems where you have a very small number of examples for each class. So I wrote the first paper on that subject back in 2000. I called it Learning from One Example. And I defined this modern paradigm that's now used in like a large number. I would say at every conference now there's several hundred papers on learning from a small number of examples, because people realize that figuring out how to learn from a small number of examples is sort of a core element of human intelligence. And if we want things that act like human beings and are generally intelligent, that you can't, I used to joke with my students, do you remember the day your mommy took you out and showed you 1,000 pictures of an apple? No, of course not, because she just, she was eating an apple and she just said, that's an apple. And that's probably the last time you ever needed to hear that was an apple, right? So if we want artificial intelligence systems to behave like human beings, they better be able to pick up concepts quickly. Now, if you talk to old-time statisticians, they would say that's impossible because you can't determine anything from a single example. But if you have what's called the right inductive bias, if you can learn from other things you've learned before, like if I can learn from my handwritten digit experience that digits are allowed to rotate and shift and change size without changing their identity, then when I see a new type of character, like a euro symbol, I can infer that those same properties are likely true. And that gives me a really good head start in learning about that stuff, okay? So the summary of the kinds of problems I'm interested in are problems where humans are showing much stronger performance than machines. For example, by being only needed one example of something instead of 6,000 to learn it. And then trying to figure out what is it that people are leveraging in order to be that much better. Now, of course, you're living in 2023 where computers have gotten really good at a lot of stuff and sometimes even better than humans, but there's still a lot of examples of stuff where people are much, much better than computers. So I'll give you an example. If I hold up a picture of, Joe Biden or something, and I ask you, do you think that's Joe Biden? Of course, you'll get it right, and so will a lot of computer programs. But if I ask you, how certain are you that it's Joe Biden? You will probably say, I'm 100% certain. And when you say you're 100% certain, you almost never make a mistake. But computers, when they say they're 100% certain, they actually make a lot of mistakes. So this is called being miscalibrated. They're not very good at assessing their own confidence. And that's a big problem because, if you're using face recognition in something like police work, you'd like to be able to ask the computer vision algorithm, how certain are you that these two people are a match? Because if you're not certain, I don't want to use the evidence. But if you are certain, I do want to use it. And computers are really terrible at this. So I'm just giving you an example of something that where people are still, generally speaking, quite a bit better at assessing their own level of confidence, which is super important. So I'm going to talk about this work called unsupervised hard example mining from videos for improved object detection. And here are three of the students who worked on it. Actually, So Young on the left here is now faculty up at Dartmouth. And on the right here is Huizhu Zhang, and he's a professor at Northeastern. Here are some of the papers that came out of this work. If you want to reference those later, you can find them on my website if you want. So there is this process that we use all the time in machine learning and computer vision called supervised learning. And the way it works is you have some classes you'd like to be able to recognize, whether they're apples and bananas and pears for a fruit detector, or in our case, we're going to be looking at a face detector, which is supposed to find all the faces in an image and put a box around them. Now, we're going to have two classes. If you think of the infinite number, or nearly infinite number of rectangles you could put down in an image, every rectangle you could consider to be either on a face or not on a face. And our goal is going to be to scan across an image, and whenever we see a face, put a box around it. So that's called face detection. Now, in order to build such a face detector, we need training data to give examples to the computer of what's a face and what's not a face. Okay, so here I've shown you one image that has three faces in it. So the white boxes are showing you some places that we know there are faces. And you can think of every other rectangle where there's not a white box in the image as being an example of a non-face, right? Like a rectangle on the blue shirt would be a non-face. So this provides data for a machine learning algorithm so that it can be trained to guess whether something is a face or not, okay? So what we do is we have some model, like a neural network that might have millions of parameters, and we start it with these random parameters, and we guess whether each little chunk of the image is a face or not a face. And we also have maybe thousands and thousands of images so that we can have many thousands of face examples and many millions of examples of non-faces. And we keep getting the algorithm to guess whether something is a face or not, and then we adjust the parameters of our model using a technique called gradient descent to improve our score on the test, okay? So we just keep taking this test over and over and over to see if we can guess which things are faces and which are not. And every time we take the test, we tweak the parameters a little bit to improve our results on the test the next time. And after this process stabilizes, we're pretty good at detecting faces, okay? So that's the general process of supervised learning, and you can use it with something like a neural network. So what's wrong with this process? Well, the more data we can gather for a particular problem, generally the better it does. If we have 1 million faces, we're going to get a better face detector than if we have 10,000 faces. And if we have 10 million faces, we'll get a better face detector than with 1 million faces in our training data. So more training data generally leads to stronger classifiers that get more answers correct, okay? Some modern machine learning algorithms want millions or billions of examples in order for them to learn various visual concepts, okay? But first, one of the big problems is this is very expensive and it's a lot of work, okay? So, you know, in order to produce images like this one that show where the faces are, you have to have a person go in and put a little box on every face, right? And to do that millions and millions of times might take you months and months and months, and you might have to pay people millions of dollars to prepare all this stuff, okay? And you still don't have as much as you want, okay? So, you know, you never have enough training data or hand-labeled training data. Another issue is that some of the collected examples don't actually help the machine learn that much. So I want to give you an analogy here. Imagine you had a math teacher and they just kept giving you one-digit addition problems over and over and over. You know, what's 1 plus 2? What's 2 plus 3? What's 3 plus 2? What's 5 plus 1? Well, after a while, you're not learning much from these examples. You need to move on to harder examples in order for your learning to continue. But if I just grab random images off the web and label faces on them, a lot of them are too easy, and the computer already gets them right. So they're not going to help me change my parameters to become better because I'm already getting those examples correct, right? If you get 100% on a test, you can't improve your score, so you're not going to learn anything. So what we need are examples that are, and if the examples are too hard, like imagine the image is just blank, it's like a black image. Well, is that a face in the dark or is it just a cucumber? I mean, we have no idea, right? So, so examples that are too hard don't help either. What we need are examples that are really faces, but they're a little bit hard to tell are faces. And we also need some things that aren't faces, but they might look a little bit like faces. Like imagine, you know, you look up at the sky, you see a cloud, it looks like a face, but you know it's not really a face. Okay, so that might be a hard example. Finding these kinds of just right examples, or what I'm calling Goldilocks examples, requires even more work than just labeling faces. Okay, you got to look out for things that are, you know, a little bit challenging, which might only be 1 in every 100 images. So now we're looking at really doing an enormous amount of work to get the training data required for this such a system. Okay, so I'm going to be talking about these hard examples that are useful in machine learning, and they're called hard positives or hard negatives, depending upon. So hard positive is an example of a face, which is why it's called a positive, that the current algorithm you have gets wrong. Okay, we'll call that a hard positive. So the algorithm might say it's not a face, but it really is a face. So that's called a hard positive. There's also hard negatives, which are things that are not actually faces, but the algorithm says it is a face. Okay, here's some examples of these. That's a good question. We're going to use both normal examples and hard negative examples and hard positive examples. And what I'm actually going to be talking about is starting off with a system that works pretty well, and it gets most of the easy faces, but we're trying to make it better by focusing on the hard examples. So unlike the previous examples, which were labeled by a human being, these examples were detected by a neural network trained face detector. Okay, and there are 3 consecutive frames from a movie. It's a Woody Allen movie. I forget the name of it, but in the first frame here, the algorithm detected 1 face, and it was clearly a real face. So hooray, it did a good job. In the second frame, it detected 2 faces, the same person's face again, and somebody's hand that was moving really quickly. Now, so you can see it in the red box. So why would it think that that hand was a face? Well, first of all, it's the color of skin, of this person's skin, which makes it more likely to be detected. And the truth is, it's very hard to say why the algorithm thought this was a face, because it's very hard to peer into neural networks and understand what they're doing. But it's got a lot of lines in it, and it's the right colors and shades to be detected as a face in this example, but it's clearly wrong. So this is what we call a hard negative. It's not a face, but the algorithm thought it was a face. Okay, and then in the third frame, it once again is only detecting the face. So what we're going to do is we're going to try to leverage the behavior of the algorithm on this video to automatically generate hard examples for continued training. So here's what we're going to try to do. We're going to try to take an existing detector, in this case, either a face detector or a pedestrian detector, and we're going to retrain it with hard examples. Okay, I've already talked about what that means. But how are we going to get those hard examples? We're going to obtain the hard examples automatically by using videos that nobody has ever labeled in an unsupervised manner. So the paper is about a process of taking a video, like a movie, and generating automatically a large set of hard examples, which we can then use to retrain our detector. So how are we going to obtain these examples? We're going to use what I call temporal consistency cues in the video to find detected errors. I'll explain what I mean by that in just a minute. And this is going to result in a fully automated process that can help us produce millions and millions of these hard examples without any human effort, okay? And that's going to enable us to train better detectors. And then after we train these, we're going to retrain our baseline with these automatically obtained examples. So we start with on the step on the left where we train a face detector using normal labeled data, okay? Maybe we have 10,000 examples and we're going to use it. We're going to train a detector. That detector is going to work pretty well most of the time. It'll say that most faces are faces and most non-faces are not faces, but sometimes it's going to make mistakes. And we're going to try to leverage these mistakes in a particular way. We're going to use our baseline detector to make predictions on unlabeled video. Then we're going to do what I call hard example mining, and we're going to use those hard examples to retrain the baseline detector and get better performance. So let's go back to this figure I showed you before. And I'm going to define something called a flicker in videos, okay? So imagine as I'm running a face detector in video, you could imagine running a face detector on my live image right now. It would be going detect, 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 and maybe 500 times in a row, it would detect my face. But if, for example, I reach up and I pull off my glasses, my hand might occlude my face enough to cause the detector to fail. Or alternatively, something might show up like my fist that looks a little bit like a face, and that might get detected as a true face. So this is all based on a super simple idea, which is if you run a detector on a video, you expect the output to be consistent, right? Face, 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 or not face, not face, not face, not face, not face, right? But so any time, if you analyze a sequence of frames like the frames shown here, you can see we have the face is consistently detected, but the red box shows up out of nowhere. So the idea is that if something shows up in one frame and one frame only, which is what we call a flicker, it's probably not a real face. So these are called flickers. And it turns out, not surprisingly, they're really easy to detect. You can write a program that says, hey, if I didn't see something in this location in the previous frame, and I didn't see it in the future frame, but I did see it in this frame, that's not consistent behavior. So it's probably an error. So what should you do with that error? Well, these are what I would call on flickers, where the red box is showing up out of nowhere for one frame and then going away. So that's a hard negative. It's probably not a face because it was detected only once. So what you do is you just copy it to the side and say, hey, I'm going to use that later to train my new face detection algorithm, because it's a nice example because it confused this detector. I need to train a detector that does not get confused about that, okay? So there's a similar example on the bottom about pedestrians. It's hard to see it, so I'm going to skip on to the next example. So this is an example of what we call an off flicker, where you had a series of successful detections, yellow, 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 and then no detection, and then yellow and yellow again. And when you see this kind of pattern in a video in the detections, then in this case, you can usually assume that The example was a face, but it was not detected. So that's called a hard positive. And in this case, the shadow got somebody else was talking about shadows, right? In this case, the shadow got a little bit too strong for the detector, and so it didn't work in that particular frame. We want to give it that example again and say, hey, you should have detected something here. So adjust your parameters so that you would have detected it. So that's the whole insight behind this paper. It's really that if you take an existing detector and you run it on hundreds and hundreds of videos, you can search for these flickers that are either hard positives or hard negatives. You can copy them to the side. And then when you have a million of them, there's no reason you can't get a million of them. You might just have to run your program for a week on 1,000 random videos. You collect a million of these, and then now you've got your training data, and you just retrain your detector on these challenging examples. And guess what? It gets better. I think this is a good time for me to show you this video. So here we go. We're slowing down. We say, bam, okay. See, his hand got detected as a false positive. And so we set it aside as a hard example. We'll keep going here. Okay, here's another one. And we'll get the back of his neck, right? Yeah. Okay, so that's another example of a hard positive. I mean, a hard negative, sorry. So we set that aside again. So we just keep running this and collecting these examples. I'll let it go for a little bit here so you can see how it works. You can see often hands get detected as false faces. It's hard for the algorithms to understand that hands are not faces, which seems weird, but that's the way it is. There's more hands to the face. Very good question. I think so that is that's what we call the purity issue. So if we mark 100 faces as errors, or well, we said they weren't faces, but the algorithm said they were, but some of them actually were faces. Let's say 10 out of 100 actually were faces. So we say that the purity of correct IDs was 90%, but there were 10 errors. So that does happen. And that makes the training a little bit less effective because we've got some incorrect examples in the training. So I'll tell you an interesting story, which is about 2 years after we published this paper, I saw a presentation on the autonomous driving at Tesla, and they were using the exact same method that I'm presenting here, but instead of running it fully automatically, they were paying people to filter through the hard examples and throw out the bad ones, okay? So that's what I would call a partially supervised method. They were obtaining the hard examples automatically, but then they were having them corrected by a human being. Whereas our method was fully automatic. The baseline, the performance of the baseline detector is shown in the upper left. So you can see there's a person leaning over backwards, which is a hard example for this system to detect. And the baseline detector got it wrong. And we have 3 other versions of our system. This one is called, it included training on hard negatives. This one included the hard positives and got it correct. And then this one included both hard negatives and hard positives. So you can see that the fully trained system based on our method was able to pick up on that face, okay? So I'll just give you a couple more of these examples. Okay. So here is a tiny piece of this soldier's hand that was detected as a face by the baseline system. Why did it detect it as a face? Nobody knows. That's the result that came out of training, okay? But when you go down here and you look at the example we retrained based on the hard negatives and hard positives, oh, this arrow is actually pointing at the wrong place. Sorry, it should be pointing over here. Let's move it over here. There we go. It did not get this example wrong anymore, okay? So those are just a couple of examples of how by retraining the system based on this automatically obtained data that you can improve the performance of these systems. Now, they still have a long way to go, but personally, I'm more interested in figuring out how to do this automatically than I am in paying, low-paid workers, thousands of dollars to produce millions of examples. Because, one of the hallmarks of human learning is that people can self-improve, right? So this is the kind of algorithm that you can imagine a person using, right? Like if you're looking at a scene and you think you see something, you might look at it again and say, gee, I thought I saw something, but now that I look at it over and over and over, I'm not getting a reliable detection out of it. So whatever I saw before must have just been a trick of the lighting or something. You see what I'm saying? So it's sort of, you can make an argument that this is like human style learning, trying to learn from your own mistakes and the inconsistency of your own perceptual system. That's a great question, and it's very difficult to answer. So one of the things that happens is if you took some of these images and you blew them up really big and you turned up the contrast, you might see something that looked like a face. So because the algorithms are digital, they themselves will do this internal like normalizing and contrast enhancement and stuff like that. And sometimes they'll hallucinate a face out of almost nothing. And you might say, well, why don't we just get rid of that? But if you get rid of it, then they start making errors on faces, on true faces. So it's very hard to find the balance. And, one of the reasons you might see a face, even though the image is very poor quality, is because it's sitting on top of a body, right? Like you expect to see a face on top of a body. Whereas a lot of these detection algorithms, they're not as good at taking in the total context and saying like, well, it makes sense to see a face right here because this is a car and there has to be somebody driving the car, and that's about where a face would be. So even though there's not very good visual evidence for it, I'm going to guess that it is a face. So that's the kind of thing where human perception tends to still outperform the machines. That's another great question. So that really gets into a lot of the technical details. So first of all, the box that it puts on the face is not necessarily the same box it uses as context. Like it might use a wider box for context, but then only put the box on where it thinks the face is. So a lot of the best algorithms today do use a bigger box for context than the place that they're actually analyzing as a face. So you have to get into the details of every algorithm to see what they're using as context relative to the box that they're putting the face around. But it's often bigger. So that's a great question. Well, there's kind of a long story here. I'll try to give you like the 2 or 3 minute version. So when I started working on face recognition back in like 2005 or something like that, it really did not work very well. And some companies were trying to sell it, but they weren't getting that much traction, and they were making some sales, but it wasn't that great. Okay. In 2012, there was sort of a new renaissance of neural networks. It came out of Jeff Hinton's lab in Toronto. And that's when computer vision really came into the mainstream, because it started being able to do stuff that was pretty impressive, like some autonomous driving, face recognition, object recognition, stuff like that. So a couple of years after that, a lot of vendors had very strong face recognition systems, and they started selling it to police departments all over the place. And while the systems were pretty impressive, they still made a lot of mistakes, okay? So people started getting like falsely arrested because of the mistakes of face recognition systems. And this is a huge problem. And one of the big issues is that even if a police officer was trying to do the right thing, they don't really understand the degree to which these systems can be or should be trusted. And then you've got a vendor who's selling the software who's saying, this thing never makes mistakes. And you're like, okay, sure, it doesn't. Right. But so the problem is, it was an unregulated product in a space that honestly should be severely regulated, because it's like drugs, right? You can't buy drugs, at least not legally, without having them be approved by the Food and Drug Administration, because otherwise the vendors would have too much power and they could sell stuff that wasn't safe and effective. So because I do a lot of research in face recognition, and I also have a background in medical devices. So I have a lot of experience dealing with the Food and Drug Administration and regulating products, medical products. So I have been pushing the idea that face recognition technology should be regulated like medical products. And so that's been like a constant thread of my work. If you go to my webpage, you'll see papers I wrote about regulating face recognition stuff. And so they're trying to produce legislation in Massachusetts that it allows the police to use face recognition, but it requires them to do it in a controlled way. For example, you have to get a warrant before you can test somebody's face against something else. And you have to have probable cause, and you have to be transparent about the software you're using, and all this kind of stuff. It's kind of common sense stuff, and the police now agree with it. It's supported by the police. It's supported by civil rights advocates, and it's supported by technologists. So I am the main technical contact behind that legislation. So I've been asked to testify about it a couple of times before the Massachusetts State House. The main purpose is to get the bill passed so that we can implement some of these regulations. And actually, the bill that was put forward in Massachusetts has already been passed. A copycat bill was passed in Minnesota, and it was also passed in Maine. And it's also been introduced at the federal level by a congressman from California. So ironically, even though we were the first to put this forward in this particular form, a lot of other people have picked it up and passed it while we've been arguing about it. So whenever they ask me to come support it, I say, sure, just tell me when to sign on and I'll give you my spiel. So that's what I was doing today.